Hello guys, in this video we are going to cover the basic information about TLC, Thin Layer Chromatography. Specifically, we will explore what TLC is, how it's made, how it works, and what is used for. Let's dive in. So what exactly is TLC? Well, TLC stands for Thin Layer Chromatography. To understand what TLC is, we need to break down these two words, chromatography and thin layer. Firstly, what is chromatography? Chromatography is a technique used in organic chemistry laboratories to purify compounds. It involves a stationary phase, which is usually solid, and a mobile phase, which is usually a fluid, such as a liquid and a gas. So chromatography is a technique used to separate compounds. Now, what does thin layer mean? Before understanding that, it's important to note that chromatography is divided into various classes based on different parameters, such as the type of mobile phase and so on. Now, thin layer chromatography falls under the classification of adsorption chromatography. Why? Because the interaction between the stationary phase and the compound to be purified is an adsorption interaction, meaning it occurs at the surface of the solid. So we shouldn't confuse the term adsorption with the term absorption. Adsorption refers to an interaction with a surface of a solid, whereas absorption refers to interaction with entire volume of a substance. So, in summary, TLC is a technique used to separate compounds based on their interactions with a thin solid layer. Alright, so we have established that thin layer chromatography falls under adsorption chromatography. However, adsorption chromatography can be further divided into two classes, column chromatography and thin layer chromatography. What's the difference between the two? The main distinction lies in the support where the stationary phase is held. In column chromatography, the stationary phase is packed inside a glass column, and this technique is used to separate large quantities of compounds. On the other hand, in thin layer chromatography, which we are discussing in this video, the support is a very thin material onto which the stationary phase is applied. So now we understand the terms chromatography and thin layer. So we understand what TLC is. It's a technique used to purify compounds, the word chromatography, but done on a thin layer support, is on almost two-dimensional surface. This is because small quantities are used, making this technique more suitable for diagnostic purposes rather than separating large quantities of compounds. In such cases, column chromatography would be more appropriate. To sum all up, TLC equals purification of small amount of compounds for diagnostic purposes. Alright, let's take now a close look at how TLC is made. TLC consists of a plate onto which the adsorbent material is deposited, which is the stationary phase, and the stationary phase is mixed with a binder such as gypsum, starch, etc. to provide compactness and stability. But that's not all. Besides being mixed with a binder, the stationary phase is also mixed with a fluorescence indicator, which will be useful during TLC detection. Think of it as a kind of dye that causes the TLC to glow green when placed under a lamp under a specific wavelength. Now, the stationary phase with this other material mixed with is placed on a support. And what is this support made of? Well, there are various types of materials used for the support. Indeed, you can find TLC on glass support, or you can find TLC or even plastic support. However, TLCs also vary in size. For example, you can find this, which is a TLC 20 x 20 cm on a glass support, or you can find also a smaller one, like 5 x 10 cm which is actually very common. Okay, thank you, bye. Thank you, bye. Go! Finally. Choosing the right TLC depends on your intended use. Typically, for everyday laboratory use, aluminum TLCs are common. Either large sheets that you can easily cut, or those already available in the standard size 5 times 10 cm. Besides the dimension of TLC, the most important distinguishing factor between TLCs is the type of stationary phase. So what kind of stationary phases are used for TLC? Generally, the most common stationary phase you will likely find in your lab is silica gel. This is because it's cheap and effective with most polar organic compounds, as it's a polar stationary phase. However, there are also other stationary phases that can be used whenever silica gel doesn't work. These include aluminum, cellulose, and fluorosil. Alright, now we have understood how TLC are made, but let's dive into how they work. Imagine we have a classic 5 times 10 cm TLC. How does it work? We dissolve our sample in a suitable solvent, which should be also highly volatile, it's better, and then we spot a small portion of this solution onto our TLC plate. The solvent, if it's volatile, should evaporate quickly, so the sample has been spotted at the base of the TLC, in what's called the loading line, in a small circle with a diameter ranging from 1 to 2 mm. Now, here we are showing an example of spotting just one sample, but you could spot many on the loading line. But let's continue. After spotting our sample, we prepare the elution chamber, a glass container with a lid. Paradoxically, it can be also a jar, as long as there is a lid. Inside the elution chamber, we place the elution mixture, a specific mixture of 1 or 2 solvents chosen appropriately for the separation. Typically, an elution mixture consists of a non-polar solvent plus a polar solvent. Just to understand, a common eluent mixture is A22 hexane, non-polar solvent, ethyl acetate, polar solvent. So this pre-prepared eluent mixture is added to the elution chamber. Next, we place the TLC inside the elution chamber, ensuring that the bottom of the TLC touches the solvent, but without letting the solvent pass the loading line. That's very important, otherwise our sample will simply dissolve in the eluent mixture and we will lose it. So we take care of this. Then we close the elution chamber with the lid, and what happens? The solvent gradually rises up the TLC through capillary action. Once it's risen a few centimeters from the top of the TLC plate, we promptly remove the TLC, mark the solvent line with a pencil before the solvent evaporates, and our TLC is done. Alright, let me explain why this process isn't just trivial. Because we have apparently simply allowed the solvent to migrate up the TLC through capillary action. But what's the point of that? Well, that's because I haven't told you yet what happened to our sample during elution, meaning the migration of the solvent from the bottom to the top of the TLC via capillarity. What happened to our sample? The sample in this case is subjected to 2 forces. An external force from the solvent, which wants to carry our sample upward, dragging it towards the top, and the other force is from the sample itself, resisting this behavior of the solvent. Crazy behavior. The sample's resistance depends on how strongly it interacts with the stationary phase. So our poor sample tends to cling the stationary phase, but its ability to do so depends on its polarity, as we are typically dealing with polar stationary phases. The more polar the sample is, the more it will interact with the polar stationary phase. and resist the threats of the solvent to carry it to the top. So at the end of the chromatography run of our TLC, our sample will be displaced from its initial position and will be found higher up if it has little force to interact with the stationary phase, while it will be found lower down if it has a strong force to cling to the stationary phase. This is put simply. Of course, I can adjust the position of my sample on the TLC by modulating the elution mixture. So I will find my sample higher or lower depending on how I have selected the elution mixture. The more polar the elution mixture, the more I'll be able to push even polar compounds upwards. The less polar the elution mixture, the more I will retain polar compounds lower down, because they will have more force to cling to the stationary phase in this case. And if the solvent itself becomes polar, it becomes a problem for our sample, because at that point the sample will struggle to cling to the stationary phase, since the solvent itself is polar and will drag it upwards even more. Alright, this is the basic concept of how TLC works. However, we have used an example of a clean compound where there was only one spot on TLC. But what happens if we spot a sample onto TLC which is not pure, meaning it's composite of multiple compounds? Well, the TLC will separate all of these compounds. So after elution, instead of seeing just one spot, we will see multiple spots, one for each compound in the mixture. In the mixture we spotted on TLC. However, there is a challenge with TLC, because not all samples are visible to the naked eye. Some compounds are colored, and in this case it's possible to see them. But unfortunately, in the everyday life of organic chemistry lab, we often deal with compounds that are not colored. I know it's depressing, but that's how it is. So how do we see them on TLC? In most cases, we use a UV lamp, which allows us to see our spots as dark patches. However, we will only see the spots that are able to absorb the UV light. If our compound does not absorb the UV wavelengths, we might use other detection techniques, such as using dyes. So in this case, you can immerse your TLC in a dye solution and see the spots emerge thanks to the dye. So now we have seen how TLC works in general. But what is used for? Well, TLC has various purposes. One of them could be find the elution mixture for column chromatography, the technique I mentioned earlier, which allows to purify compounds in large quantities. Since TLC is a smaller scale version of column chromatography, it can be used with the same stationary phase as a small scale model for column chromatography. So I can spot small quantities of my sample on TLC and try various elution mixtures to see which one separates my compounds best, and therefore which elution mixture is best for the column chromatography. TLC is also used to monitor the progress of column chromatography. Indeed, I can perform TLC of the various fractions coming out from the column chromatography and see when my samples comes out of the column and if it comes out pure. This is because with TLC I can also verify the purity of compounds. If I see a single band on my TLC after elution, this means that my compound is pure. But if I see multiple bands, it means it's impure and needs to be cleaned up. I can also use TLC to recognize unknown compounds if I have a reference. By spotting both the reference and the unknown compounds on TLC, if I see two bands at the same height after elution, it means that the sample I spotted is likely the same as the reference. Last but not the least, TLC is used to monitor reactions. Thanks to TLC, I can determine if a reaction is over and if my product has formed. Well guys, that's all for this video. If you want to delve into how to perform a TLC directly in the lab, how to choose elution mixtures and stationary phases, how to solve the most common TLC problems, what are two-dimensional TLC, and much more, take a look at the Organic Chemistry Laboratory course that I have linked in the description. Until the next video.